question 1 then gave us this alcohol and asked for 3 things: name, skeletal formula and molecular formula. Some people lost marks simply because they did 2 out of 3, so always read the question carefully, make sure you do everything that it asks you to do. First of all, the name. Well, you can see that the longest continuous chain, let's mark it on here, is 3 carbons. So we got 1, 2, 3. So that gives you prop. It's saturated, there are no carbon-carbon double bonds, so it's an. And then we're going to start numbering at this end because it's an alcohol, so we're going to have ol on the end, and that keeps the number as small as possible. So it's going to be 1, 2, 3, and 1 with the OH is 1 ol. Okay, so if it was just that chain, that would be propan 1 ol, but carbon 2 has an extra methyl group attached as a branch, so it's 2 methyl propan 1 ol. Okay, you must make sure you've got both of the numbers in there. Skeletal formula, so we've got chain of 3, is like that, with the OH on the end, and the branch at carbon 2 is like that. And the molecular formula, we've got 4 carbons, so it's C4. Now we have got 10 hydrogens, because you've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's C4H10, and then 1 oxygen is O. A number of people wrote C4H9OH. That's a sort of formula, but it's not a molecular formula. In a molecular formula, the hydrogen has to be included with all the other hydrogens, because that's all a molecular formula is. It's just a list of how many elements of each atom are in the molecule. So that's not a molecular formula. It's not a very useful formula anyway, because C4H9 is ambiguous. You can't tell if it's straight or branched. So generally that is not a formula that you should ever really be using. So that was the answer. So in part B, it asked you to explain with the aid of a diagram why this substance is soluble in water. Generally when it says with the aid of a diagram, it means it wants a diagram, but it wants some words as well. It would just say draw a diagram if that was all it wanted. So you need to do both things. So to put it in words, all you have to say is that it can form hydrogen bonds to water molecules. Okay, that's the reason. So for something to dissolve in water, it has to be able to persuade the water molecules to separate from one another, to break some of the hydrogen bonds they form to one another, and it can only do that if the molecules can offer something sort of equally good in return, and in this case the molecule can, because it can also form hydrogen bonds. Now when you come to do the diagram, the best way to do these is to remember the diagram for water, which you hopefully have learned, because this was one of the key things that we practiced. So remember, you have 2 water molecules and you draw the hydrogen bonding between them. We learnt to draw something like this. And the key features of that are, first of all, that it's an attraction between dipoles. So you've got to show the dipoles, not just the delta plus and delta minus there, but the polarity of the molecule, so the delta plus and delta minus there, and you might as well put them all on. The hydrogen bond is shown as a dashed line or a dotted line between delta minus on one, delta plus on the other, and it's supposed to point at a lone pair on the oxygen, because, if you like, that's where the sort of delta negative charge is focused. So that was the diagram you learned for water, and all you have to do here is to think, yeah, but one of these molecules is water, the other one is 2-methyl-propan-1-ol, so you just convert it into 2-methyl-propan-1-ol, and so you just choose one of them and you just say, right, well, if it's 2-methyl-propan-1-ol, it's that, and that's it, job done. In part C, it introduces a hydrocarbon, C4H8, which is called Y, and it tells us that this can be converted into 2-methyl-propan-1-ol. So clearly this is going to be the alkene, and you know that you can add steam across the carbon-carbon double bond in an alkene to stick a hydrogen on one end and an OH on the other, and so that's going to be the reaction that we're looking for. So Y is going to be this, so it has the same carbon framework as 2-methylpropan-1-ol, but instead of a single bond here, it has a double bond here, so that it can add H to that end and OH to this end to give you that product. So the reaction is plus H2O. Okay, so that's the equation that you need, and then the conditions for that are that you need steam and you need a phosphoric acid catalyst. Okay, so this is not an easy reaction to get it to work. So you need both a catalyst and pretty high temperature to get it to work. So you've got to learn those conditions. So that's all you needed for the answer. You may have thought, yeah, but that's not going to work very well, because remember, when you add steam across that double bond, it could add either way round, like that, and the product we want would be formed via a primary carbocation, because you'd have to have the positive charge there in order to get the OH minus to join onto it to make that, whereas the alternative would be a tertiary one. So actually this would be a rubbish method of making this compound, because the major product would very definitely be the alternative alcohol, which would be this one. So if you thought about that, that was great, that was a good job, but in fact this was the only possible answer anyway, so you just had to go with it. Question D then asked you to find a way to make this compound in 2 steps, starting from an alkane. So the alkane clearly needs to have the right carbon framework, so it'll have the 4 carbons in place, it just won't have the OH group. So you're going to start from 2-methylpropane, which is that. And when you do questions like this, it's important that you don't make up reactions. Some people ripped hydrogen out of that to turn it into an alkene and then did the same reaction we had in the previous thing. The trouble with that is that's not a standard reaction, it's not a reaction you've learned. It is true that compound, if you take it up to very high temperatures, might well lose hydrogen, but it might do other things as well, because you might get all sorts of cracking reactions going on. So that's not a way to go. You have to use the reactions that we've learnt, not make them up. And the only reaction you've learnt apart from burning for alkanes is radical substitution. So that's going to have to be the way to go. So you start by reacting with either bromine or chlorine. Take your choice, it doesn't make any difference as far as we're concerned. So you could substitute in then a bromine where the OH needs to be, and HBr will be the other product. So that would be the first step, and remember that requires UV light. Okay, so that's radical substitution. We substitute a bromine in place of a hydrogen. So we haven't got the OH, but we have got something at the right position. Wouldn't be a perfect reaction because a little bit of the bromine might substitute here instead, but actually it shouldn't be too bad because statistically it's much more likely that one of these hydrogens in these 3 positions would substitute, and that would give you the product that you want. So that'd be the first step. And then you think, okay, so how do I turn that into that? And again, that's a reaction that you've learned, because this is just hydrolysis of a haloalkane. So you need that plus sodium hydroxide will give you that plus sodium bromide. Okay, so that's the standard substitution reaction. The key condition for that is that it needs to be aqueous sodium hydroxide. 1 or 2 people just put plus water, gives you that plus HBr. Now that you might or might not get marks for, because it does happen, and we do learn that haloalkanes react with water in the same way that they react with aqueous alkali, just more slowly. The problem is that it is a lot more slowly. So it's not a very good way of doing it, and it's possible therefore that they wouldn't give you the marks. So yes, you need to be aware that you can get that hydrolysis reaction just with water, but don't use it when you're asked to suggest a synthesis, use the aqueous alkali, because that's the standard method that works efficiently and quickly. So question D introduces this transformation that we can take 2-methylpropan-1-ol, compound X, and turn it into this. So it asked you, first of all, what was the name for the new functional group that we've created? And the functional group obviously is the COOH group, and that's called carboxylic acid. Now, several people just called it a carboxyl group, and that probably comes from having learnt that in biology. It's just one of those annoying things that biologists use the shortened form carboxyl or carboxy, but in chemistry you're supposed to use the full term carboxylic acid, so you just have to remember that. And then it asked for the reagent. Reagent means what you react it with. So it's not necessarily just the substance that it reacts with, but it's whatever other key components need to be in that solution. So the answer is not just potassium dichromate, it's aqueous acidic potassium dichromate. And you need all of those components. Okay, it's got to be aqueous, it's got to have added acid, as well as having the potassium dichromate there. You could name a specific acid and say aqueous potassium dichromate plus sulfuric acid. That's what people normally use, and that would be fine, but you can't miss out any of those individual terms. So that whole thing is what you need to learn as the reagent for oxidation. And then it wanted a balanced equation, and this is using this trick of using the magic oxygen to represent the oxidizing agent, which is what you always do in organic chemistry, because the details of how this oxidizes and what it gets turned into are quite complicated and are not of any interest really from the organic point of view, so we just keep it simple by using that. Now the thing you have to remember is that when you go from a primary alcohol to a carboxylic acid, that's a double oxidation, because you're going first to an aldehyde and then from the aldehyde to the carboxylic acid. So you need two magic oxygens, okay, one to get from there to the aldehyde stage, and then the second one to get to the carboxylic acid. And the other thing you have to remember is that in that first stage of oxidation, you're not adding an extra oxygen in. What you're doing is taking two hydrogens out, that one and one from this carbon here, and those two hydrogens react with the first magic oxygen to make water. So that's your product. The second oxidation just adds the extra oxygen in, so there's only one water produced. Okay, so part 4 then wants the details of the experimental method that you use to convert your alcohol to a carboxylic acid using the reaction that you've just described. So the important issue here is to remember, as I say, that this is a double stage oxidation. You've got to go first to an aldehyde, and then the aldehyde gets converted into the carboxylic acid. And you need an experimental setup which will make sure that you don't stop at the aldehyde stage. So the technique you use is called reflux. And that's a very important word. So you need to practice drawing the diagrams both for reflux, which is what you want here, but also for distillation, which is the alternative method that we'll mention in a minute. So in reflux, the key component you have is something which you draw like this. And you have to label it, and it's called a condenser. So when you draw these diagrams, the thing to do is to imagine you're drawing a slice through the middle of the apparatus. It's called a cross-section view. So you're not sort of drawing a perspective of what it looks like from the outside, you're imagining it sliced through the middle and saying, what would you see? So this is a tube running up through the middle, and that's going to be in contact with the flask, which we'll draw in a minute. And then round the outside of it, this compartment on both sides of it is really a cylindrical compartment, goes all the way around the tube, and that's a water jacket. So what you also need to label is that you need to have cold water flowing through it, and it must go in at the bottom and out at the top, because that's the only way to get it to flow efficiently and fill up the whole condenser. Okay, so you've got to draw that, make sure that it's open at the top. We'll just talk about that a bit more in a minute, but let's draw the flask on. I have a choice of two types of flask. You can draw one like that, which is called a pear-shaped flask, in which case you label it pear-shaped flask. Or if you preferred, you could have one that looked like this, in which case you label it round-bottomed flask. But either way, it needs to have the condenser stuck in the top of it like that. You can't have a conical flask, which is one of these. Okay, that's not used in these kind of organic things, so that's no good. But round bottom or pear-shaped would be fine. And I say the important thing is that this is all an open system, so what you shouldn't do is draw lines there and there, because that would imply that this is a closed chamber, that the vapour is trapped in the flask here. Or if you draw it open there but closed at the top, then again this whole thing would be closed and the vapour would be trapped in there by this wall at the top. And of course the trouble with that is that as you heat it, the vapour will expand and the apparatus will explode. So it's meant to be open at the top there, like that. And then you just draw in your reaction mixture. It's a good idea to put some anti-bumping granules in, so you could just draw those. They just enable it to boil smoothly. Usually they don't require those in the mark scheme, but it's good practice, so yeah, put those in. And then you don't have to draw the Bunsen burner or anything, you don't have to draw clamps or anything, but you do need to indicate that you heat it from below like that. Okay, so that's basically the sort of diagram you want. So it's relatively simple, but it's not a drawing, you know, of what it would look like from the outside. You've got to get used to drawing this cross-section thing, like that. So, to get full marks for that, you needed the word reflux, you needed a reasonable diagram, and then you needed the key labels, condenser and pear-shaped flask, and show the heating and show the direction of water flow. Part 5, it asks about the colour change that takes place while you're doing that oxidation. So the colour change you need to remember is that the solution changes from orange to green. That's nothing to do with the alcohol. The alcohol and the carboxylic acid are all colourless. It's the dichromate which is orange. And of course when the alcohol gets oxidised, the dichromate gets reduced, because it's just like any redox reaction, you can't have one without the other. So the dichromate is reduced to chromium 3+, which is what makes it green. So that colour change will accompany dichromate oxidising anything. It always goes from orange to green. And then in part 6, it asks you about, well, what happens if you do control the oxidation to make sure that it stops after the first stage. So we've got this compound was our starting material, and where we end up is this, which is the carboxylic acid that we've been focusing on. But remember that in order to get from there to there, it first goes through the aldehyde stage, which looks like this. Okay, so that's the first level of oxidation, and then this gets further oxidized to make the carboxylic acid. So that is called an aldehyde. And that's what you get if you just oxidize for a short time. And what the question is alluding to is, well, how would you make sure you stop after oxidizing for a short time? And the answer is that this tends to have a relatively low boiling point compared to these, because it doesn't have any OH groups, so its ability to hydrogen bond is much less. And that makes it relatively easy to just boil it off as soon as it's formed. And if instead of refluxing it, the idea in refluxing is that the vapour condenses in that condenser on the top and drips back into the reaction mixture to have another go. If you use distillation, you condense it somewhere else. Okay, you have a condenser coming off at the side and you collect the product away from the reaction mixture. So that means as soon as this is formed, it boils off, you condense it somewhere else, and there is no oxidizing agent there, so the second reaction can't happen. So aldehyde and that structure were what you needed for that answer. In part F, we have to do this, turn 2-methylpropan-1-ol into this bromoalkane. So the standard way of doing that is to use a mixture of sodium bromide and conch sulfuric acid and a bit of heat. So those are the conditions. In effect, what you get there is HBr plus extra acid catalyst. So if you just say HBr as the reagent, you might be allowed that, but it's not really the standard way of doing it. So you need to learn this. And if it was a chloroalkane you were making, then again use sodium chloride and conch sulfuric acid, because although it might work with just, you know, conch HCl or conch HBr, it doesn't work as well, because the extra H+ concentration that you get from the conch sulfuric acid makes the reaction work much better. So that is the standard condition that you need to learn. When you come to the equation though, the easiest way to do it is either to just sort of say, right, well, in effect that produces HBr, or actually I think the best way to do it is like this, to say, right, you've got your alcohol, you get H+, which comes from the conch sulfuric acid, you get Br-, which comes from the NaBr, because in effect that's right. When it comes to the mechanism, these two things react separately, so I think this is it's not just a way around the problem, it's actually the best way of showing what really happens in the reaction, is that you then get your bromoalkane, and you can see that you get water as the other product. Okay, because you get OH- there being replaced by Br-, and that combines with the H+ to form the water. So that, I think, is the best way of writing the reaction, but you can write it with just HBr in there if you want to. And what type of reaction? You can just say substitution for that one. I mean, it is actually a nucleophilic substitution, but you don't need to know the mechanism for this one, so if you just said substitution, that would be fine.